So our next speaker, and again, we'll have a panel discussion at the end where we can address some questions. Our next speaker in this session is from Intel. Our speaker today from Intel is Martin Langhammer, who's a senior principal engineer. Martin is the architect of Intel's AI-focused Stratix 10NX device. He started his career at Amdahl and IBM and later founded an IP startup that was acquired by Altera. And that's how he made his way to Intel. And Martin is going to talk about Intel's new FPGA architecture optimized for AI acceleration. So Martin, if you can go ahead and share your screen.
All right, thank you. All right, well, today I'm going to be talking about the Stratix 10NX architecture, which is the first FPGA that's been specifically designed to be a spatial AI accelerator. So we'll talk a lot about spatial today. Rather than focusing on the NX architecture, I want to get across the idea of a spatial accelerator and how that differs from everything else that everybody else is building. So the FPGA is a spatial accelerator. Every FPGA is a spatial accelerator, not just the NX, but the NX has been designed to do AI acceleration in the spatial domain. So the NX has a lot of teraflops. These have been reported before. We're going to be announcing exact speed grades and different type of performance levels shortly. There's no real, let's say, benchmark for spatiality. So we just wanted to put out these teraflop numbers so people can see that these are sort of the same number of teraflops you're going to find on GPUs of the same process node or other type of AI accelerators that are being introduced into the market. But with the spatial accelerator, what's more important is the total number of operators. And even more importantly than that, the ability to access all of these operators in parallel. And being able to access all these operators in parallel gives us a better chance of achieving a very high sustained to peak performance ratio. In fact, we've got up to about 500,000 of hard embedded AI operators. That's multipliers and adders. Those are in the INT4 mode, about half that in the INT8 mode. There's 700,000 ALMs or soft logic lookup table register combinations, which are much simpler structures than you would find in a hard arithmetic operator. So it just shows you the sort of level of arithmetic density that we've managed to put on this device. The trick now is to be able to access all of it. So FPGA is hardware you can program like software. So rather than writing software and finding a way to map it to many processor cores or threads that we might find in other AI accelerators, what we can do with the FPGA is we can program the hardware to move the data to exactly where we want it, when we want it. And we'll compare this to a few other type of AI accelerators. These happen to be ones from Intel. There's lots of different people building lots of different AI accelerators in many of these type of accelerators. So starting with the processor, the CPU is by far the most widely distributed or widely distributed AI acceleration platform. It has the most libraries, it has the most programmers. And recently we've added, or some CPUs have added low precision arithmetic, that's bfloat 16 or INT8 to make AI better. The GPU is understood to be the highest profile, most widely deployed AI accelerator. It has a lot of libraries, there's a lot of programmers, there's a lot of people who know how to use this very well. And recently, some GPUs have had tensor blocks. In other words, matrices of large numbers of low precision arithmetic added to make AI better and other type of matrix operators better. The FPGA in the middle, we'll get back to that in a minute and discuss the benefits of spatial acceleration. Moving on, there's a large number of application-specific accelerators being introduced. These are typically implemented using a large number of processor cores, sometimes with some additional hardware acceleration, often at the edge. These are mostly used for inference. And lastly, we have the matrix accelerators, which are designed to do the type of matrix, and matrix vector operations as quickly as possible. These can be both for inference or training. If we look at general purpose or purpose-built, most of these require some sort of software to be written and the software to be mapped to many threads or many processors. The FPGA is very different. What we do is we program the data flow, not the actual operations. And we could have added a whole bunch of processor cores to the FPGA just like everybody else did, but we're going to try to do AI acceleration by using every operator in parallel, which is a bit different than what other people are doing. If we look inside the NX part, we've got a large number of AI tensor blocks. That gives us up to 500,000 hard operators. There's 96 transceivers so that we can build a big network of NX devices. We've got lots of memory, including 1 or 2 stacks of HBM2. And we're using the Intel EMIB technology to use chiplets to build these very complex devices and be able to manufacture them in volume. If we look inside the NX device, there are 72 sectors. A sector consists of a number of memory blocks, a large number of soft logic blocks, and a number of these AI tensor blocks, which we'll talk about more in detail in a little bit. Each AI tensor block will have a matrix of multipliers in it. There will be 30 to 60 multipliers, depending if you're in INT8 or INT4 mode. These are set up in small dot products. There's an optional FP32 conversion and addition or accumulation in INT32 or FP32. These AI tensor blocks can be seamlessly cascaded together to build super blocks. So we can have up to 330 or 660 in INT8 or INT4 mode high tensors that are being built, and 3 of those per column. So we can aggregate these blocks together or cascade them together to build much larger tensor blocks. We'll compare the spatial concept to the parallel concept right now. And as I mentioned before, with a spatial accelerator, what we're able to do is move data to where we need it exactly when we need it. And you might ask, well, why is there a picture of a big fractal on here? Because at any level, if we're looking at the sector or the device, or in fact, a large number of devices unrolled over the data center, if we zoom in or out with a spatial accelerator, we can make it look the same. It's very extensible because we can map our data flow directly to either the device or through the entire network. So the FPGA is becoming increasingly more capable arithmetically over the last few generations. Now at any given process node, the FPGA has about the same amount of FP32 density as the GPU. We can think of these conceptually or physically, depending on the device, of tightly bound memory and floating point units. With the FPGA, we have a lot of soft logic there as well. And with the soft logic, we can build just about any function. If we need to put an elementary function or want to put an elementary function in the data path, that's very easy to do. And the use of that elementary function is zero overhead. It does not break the pipeline to put it in. It just runs alongside or in the path of the floating point unit. The same sort of flexibility can be applied to the tensor cores. The GPUs have large arrays of low precision arithmetic right now. You can write from memory into the tensor core, process it, and write back to memory. So you can see that if your matrix size lines up with your data path size, this is a very efficient way to process data. But if there's something different, if you're using very small matrices or you need to put in some elementary functions, it's a bit more difficult. With the FPGA, we can arrange tensor cores however we want. We can cascade them together, or we can cascade groups of them together. We can source and sync from any place. In fact, we can write to multiple different locations at the same time, which is quite a unique thing. We'll have a look at a couple things that the FPGA can do well, and then we'll look at the NX architecture. So what you see is what you get if you want on the FPGA. Here's a node of an RNN. We can map this exactly to the FPGA. You can see there's a number of matrix vector operations and some number of hyperbolic functions. We can set this up so that we get one output per clock after initial latency. The hyperbolic functions, the sigmoids and tanh, for example, operate point-wise on vectors. Let's say, as an example, the vector might be 64 elements wide. We can put down 64 sigmoids if we want to. We can map multiple RNN nodes, depending on the size of the RNN, to a FPGA, and then map the entire network to a network of interconnected FPGAs. We can build larger multiplies out of the AI tensor blocks as well. So this would be for the typical type of FPGA DSP applications like FIRs or FFTs, the radar applications that these FPGAs are generally used for. Rather than cascading the devices together, we do what's called aggregating them together. We can use the embedded FP32 adders or soft logic that is wrapping around these AI tensor cores, and we can build bigger multipliers like INT16. We can build FP32. We can do that with various different types of relaxations to save even more logic. We can build asymmetric multipliers. And because we are starting off with a much higher density, albeit of smaller precision multipliers, we can aggregate these to much larger or higher densities of larger precision arithmetic than is normally found on FPGAs this size. Now the power stays the same, so we get a lot better power efficiency as well. So the devices can be used for non-AI applications as well. In fact, you can mix AI and non-AI applications because you can configure different portions of the device to do whatever you want, just like any other FPGA. And now we can look at what's inside the NX architecture. As I mentioned before, there's a matrix of multipliers. There's 3 columns. Each has 10 INT8 multipliers, or we can convert this to 20 INT4 multipliers. We can configure that on a AI tensor block by tensor block basis. There's a optional shared exponent for each column, just in case we want to do floating point. Every column is added together to make a dot product, and we can optionally convert to floating point 32, IEEE single precision floating point. And we have an IEEE single precision floating point compliant adder that's available for to add or accumulate everything together. We can also optionally add or accumulate in INT32. We can cascade multiple blocks together, or we can output to the fabric in bfloat16, bfloat24, or FP32 mode. We'll use the lower precision floating points just to save routing. Routing is the most expensive and precious resource on the FPGA. The headline features, the AI tensor blocks in this case, are easily visible, but the routing, that's the thing you don't see until you need to use it. So we'll have a look at the routing issue now. AI everywhere means bandwidth everywhere, and we do have a lot of bandwidth, or so it looks like it. We've got 2 terabits per second per HBM, and there's 1 or 2 HBMs. There's 96 transceivers. We've got 35 terabytes per second in and out of the small memories, and the almost 4,000 AI tensor blocks give us 38 terabytes per second maximum bandwidth. But we don't try to use all the output bandwidth just to save routing again. We are typically cascading multiple blocks together, and we've still got 20 terabytes per second into the block, but as you will see now, that's still not enough. So we've added a lot of AI arithmetic to the block, and now we've got to figure out how to use it all, because in our spatial accelerator, The trick is to use all of it at the same time. So bandwidth everywhere means wires everywhere. And we've got, as far as multipliers go, if we look at the almost 4,000 AI tensor blocks, 30 INT8 multipliers per block, we'll need about 2 million wires to feed those all. For the last 35 or 40 years, the FPGA industry has been working on making denser and denser FPGAs. We know exactly how many wires we're able to get on a certain type of device. In this case, we've got about 317,000 wires into the AI tensor blocks. We can do a few more, but we can't do 2 million wires. So we've got to use virtual bandwidth expansion to achieve our 100% multiplier use. Now, if we look at a typical AI application, we're going to have certain matrix or matrix vector access patterns, and we can use this to preload one dimension of the tensors while streaming data through the other dimension. This works well for even very small matrices, like let's say we're doing 32 by 32, and we can keep every single multiplier full on this device continuously with this. There's various different ways of preloading the data in while the block is running as well. So the tensor mode allows us to use everything, but sometimes we need more flexibility into the multipliers, and there's several other modes we can configure the block into. Vector mode allows us to build a small dot product with both inputs to the multipliers running. You can see the impact of not being able to use the virtual bandwidth expansion. We're down to 5 or 6 multipliers, depending if we're using the floating point mode or not. In any case, we can still convert to FP32 or optionally INT32. And sometimes we need to access individual operators, and we can access the multipliers or in fact the individual FP32 adders in the scalar mode. Now, as shown on paper, we can access all multipliers at the same time. And now what we're going to do is show you a couple test cases to prove that we can do this in real life as well. First of all, we created a pathological test case. This uses 2 large buffers, one at the top and one at the side. So this is a big problem for FPGAs because we're going to be routing massive buses right across the chip. We're using 90% of the tensor blocks, and they're cascaded together to make 11 high super blocks. And we're able still to close timing 400 megahertz for this design. If we split the design up into a more realistic systolic structure, so we don't go too much further than a sector boundary, the same sort of arithmetic density gives us 520 megahertz time enclosure. Now, this is a mid-speed grade device. If we just recompiled for the high-speed grade devices, this would be over 600 megahertz, which is quite fast for a full design. Now, the other thing is we're using 90% of the tensor blocks. We're using a lot of the long wires, but not many of the short or medium wires, which means that we can use the rest of the 10% of the AI tensor blocks to build the hyperbolic functions you'd have seen earlier, or we can build any mix that we want. Again, it's an FPGA, so we can reconfigure it the way we want. Okay, that's the NX device. We'll just wrap up now. So Spatial Accelerator is something different. We're programming the data flow, not writing software. More than the teraflops, we have a large number of operators, and we're able to access them all together. And it's not just on paper, we're actually be able to fill up the part and run it in real time. Right, thank you very much.